All right. All right. Good morning. I'm just confirming my audio here. Thank you for those who have joined right away. And you have registered your attendance by penning down your registration number. So in the course of this lecture, if you have any question, comment, or concern, you can ask your question in the chat section, as well as we'll have an interactive live session on this side that I am in. If your question maybe is not cannot easily be penned down and in the chat section. All right, we have a very short session for today, just 1 hour or so, because of the reason that I raised to you. We are having postgraduate presentations, both at Pausti and JQuat, and we wouldn't like to miss. We didn't want to miss our session for this week. I believe the class as it is well constituted. I know we are supposed to be about 100 and what? 120 or thereabout. Class rep, if you can confirm that. But we can't now wait any longer. I'm seeing we're about 54. That's a third, more than a third. The others will get us along the way. Now, well, I'm going to put full screen and also remove my video. Because I know sometimes it overlaps. It makes it interferes with what I'm projecting on the screen. Good. Now, last week we started on a very interesting area. Of course, it was an introduction, but we also managed to start session 2, which was on the different types of finite element and how to formulate the finite element equations. And if you remember, we start with what we call the spring element. Okay. Sorry, this thing is not moving. Okay. The spring element. And we say this is an illustrative or demonstrative tool. Use it for introduction purposes because it's easier. It gives us some basis, some background on how to formulate these finite element equations. Before now, we can move to structural elements proper. For example, the truss element, the beam element, and then we go to the frame. All right, just something happening here with my laptop. Just a minute. Okay. Good. Now, as a recap, as a recap, we found that there are about 8 steps that we follow in formulating the finite element equations. And we said no matter what type of element that you are going to be looking into, these are the general steps. It doesn't matter how complex the structural element or our structure in itself, the complex system is, but these are the steps that we follow. I'm just hoping that you can recall them. And I've done this just to test you. So I've listed the first one, okay, where we have the discretization. We said you break down the complex system to simple finite elements, and then you select the type of element that you are going to use. And for our case, for this session, we are selecting the spring element. Then step 2 is that you select the displacement function. How does displacement vary with, of course, distance? Okay. Then number 3, you define the constitutive relation. This is the material relation. How does stress relate with strain? And also how does strain, of course, relate with the displacement? Number 4, you derive elemental stiffness matrix. The others you can continue listing in the chat box to see whether you can still recall them, because it's just a recap. Now, when you started on the finite element, one thing that you have to note when we consider spring element is that we are calling it linear. So this obeys Hooke's law within the linear range. We are not talking of hard springs or soft springs. We are considering we are considering the finite, the linear springs. So you can see here, we are considering the linear spring. That is, its force or Fs is direct proportional to the displacement. Okay, U. So you can comfortably write F is equals to or is equals to K S or Ku. Okay, K, which is the stiffness of the spring. Hard spring, as you can see, those are type of springs which they may behave linearly up to a certain range, but afterwards we require more force to get incremental elongation or displacement. And this one you can consider to be the case of when we have compression of a spring, when you are trying to compress a spring. Okay, when you are compressing it initially, force may be direct proportional to strain. You require maybe a certain amount of force, not too much, to obtain a certain displacement or contraction. But as it gets smaller, I mean, as you compress further, you find like now to get any more incremental reduction in the length, you require extra force. That's what we may refer to as the hardening. Okay, more strain, more stress, or more force is required to obtain even the least, the smallest of the increment. And now I've just used compression for illustration, but we could also have some spring when you are pulling them, like pulling them out to a certain range, force is directly proportional to strain or to elongation, okay, which is a global strain. But when you get to a certain point, after a certain point, you require more force to obtain the same elongation. Now, for the soft spring, the easiest example I can use is when, let's say you have a piece of reinforcing bar. I believe this in strength of materials you have done tensile strength test. If not, then I know in civil engineering materials you did that. So if when you are pulling this, you're testing this in a tensile machine or UTM, universal testing machine, you find like when netting start to occur, okay, when it starts to reduce, localized deformation start to occur, now you just require very small, very little force, and then enlarged elongation. We said that the material have undergone the softening phase. So we are talking of the soft spring. A and C are not of our concern in this session. What is of our concern is the linear spring, that as long as we are dealing with this spring, and this is the assumption in finite element, whatever we are doing in this course, because we said you could deal with nonlinear, we could deal with the dynamic, but for us, we restrained ourselves to static and linear case. Now, having understood that, we can now comfortably move ahead to where we started last week. And this was just a reminder or to refresh our memories on the Hooke's law, where we said if a spring is pulled, and for your understanding, right now what you're seeing is there is a force that is applied on this end, on node 1, okay? We said an element will have a node, ij, okay, ij, if it's a 2-node, okay, where I is the lower, I is less than j. So we are saying node 1, 2, okay? So 1, 2. Let's say it's a spring. The one that you are used to is the one that we have, okay, like a weighing balance, a spring balance, sorry, like that. And then we have a mass here. So what you are used to is that this end is fixed, okay? The top part is fixed. On this side, the mass is pulling it down. It's the same thing that we are illustrating here, only that now, on this fixed edge, we know what will develop is what we call reaction, okay? And the reaction in itself is a force. That's why we are assuming this part, we are removing the edge fixity and we are putting force 1. But for the sake of our understanding and from the principles of linear spring and Hooke's law, let's just consider the normal spring that is fixed. Okay, the spring in itself that is fixed on that end. So what will happen is, if you fix it on this end, okay, if it is fixed on this end, now let me replot it here for your understanding and for purposes of recap. If I fix it on this end, and then I have my spring here, okay, then I put on this end. The force I'm applying on this side, I can comfortably say F is equals to K times elongation, the resultant force. Now, what you should notice that the force here I'm talking about is the force on node 2. And that's why in our calculations, we said that this F, the resultant force, F is F2, F at node 2. And then now we applied equilibrium. If you recall, this is just a recap of last week's work. Huh? We applied the principle of equilibrium, that as long as the body will be in a state of equilibrium, and now we are talking of static equilibrium, it's not moving, we know that the summation of forces should result into 0. That is, all forces summed up, okay, should equal to 0. That's the equilibrium condition. How many forces do we have here? On this end that we had the fixity, if we remove that and replace it with force, the reaction, now that is a force on node 1. We are calling it F1. So summation of F1 plus F2 should be equals to 0, okay? All F1 is equals to negative F2, right? Now, moving on, you find now, in terms of the applied node of force, F1, F2, which we already said is the resultant force F, we have it as K U2 minus U1. Okay, we have it here. And you can rearrange, or we did rearrange it. We said F is equals to F2. You can rearrange this. Okay, if you want to start with U1, U2. Of course, it's a matter of preference. Okay, you do not want a case whereby you are starting with any node, you say node 3, 2, 4. So it's good to go in a consequential manner. Okay, 1, 2, 3, 4, and so on. And that's why we rearrange this to have F1 as equals to K into bracket U1 minus U2. Just rearranging. And then for F2, we arrange to start with U1. So we have K minus U1 plus U2. Right? So far up to that point, I know we are together. If there is any question, as I said, you can interject me by putting it in the comment section. Later on, I'll also share the link the way you can ask the question live, but only for those questions which you feel that you cannot be able to express yourself quite confidently in the using the chat section. Now, in matrix form, right? So this is how we condensed or contracted our equation, so that we have F1, F2 as a force vector, then K minus KK as a square matrix of stiffness, and then U1, U2. So this one could be written, or we said can be written in a compact form as follows. And we said these symbols, these brackets are very important. Of course, this one we call them braces, and this one are square brackets. Square meaning it's either a rectangular matrix or a square matrix. I know by now you have looked at the 2 reference books that I've given you. And in one of the books, as I said, the appendix 1 is a recap or a revision of a matrix operation in matrices, how to add, how to multiply, cross multiplication, dot multiplication, how to get the inverse by fast, how to compute the determinant, and even how to solve for simultaneous linear equations, maybe using Cramer's rule, using substitution rule, and so on and so forth. Of course, I know in an exam setup, of course, our calculators these days, you can be able to solve a matrix by just punching in numbers and get the result. But for the purposes of our understanding, of course, even though the AI is coming in, don't let it replace you. You need to know these things. At the back of your mind, you need to know how can I get a determinant of this matrix. Okay. And then we say the KE, we are using E to denote elements. Now, this is no longer the stiffness of the spring, but it's the stiffness matrix of the spring element. So the U is the displacement vector, and F is the force vector, right? So KE, this is the elemental stiffness matrix. Note the word elemental, because we are going to get to a point whereby we are talking of the whole structure. Remember the first step, discretize, break down to a finite element. And step number, I think 4 or 5, assemble now to get the global system back together. So we are going to get now the stiffness matrix for the whole system. So for the equation for the global coordinate system, or when we come to now the overall system, if you're not just talking about one element, what just changes? The equation remains the same, but what changes now is that we are denoting the force vector using a capital F, displacement vector using a capital K, and a capital U, and stiffness matrix using a capital K. Now, in some books, this is when you are writing it, you use brackets and braces, but you may find in some textbook, because of course you can be able to print in bold, then a force can just be represented by a bold capital letter. So note that difference. When you get the textbook, you may wonder why not these braces, why are they not shown? But you see they have typed them in bold. Now, going ahead, for us to understand how to assemble, move the next step, how to assemble, we can't assemble one spring element, okay? And before I forget, is that the stiffness matrix that we obtained, we saying without any further information, we cannot be able to solve this equation, okay? Because solving, this is the direct stiffness approach, or where we say that what is unknown, or what is assumed to be unknown, is the coordinate nodal displacement, okay? Now, to get this value, U1, U2, you need to, like if I just tell you, can you solve? These are two simultaneous equations. How do you go about solving them? Okay. In our case here, we need to get, or of course, make the displacement vector the subject of the formula. And by doing so, we need to pre-multiply or multiply this side by the inverse of the stiffness matrix. And to get the inverse of the stiffness matrix, you start by getting the determinant, okay? And we found that the determinant of this matrix is 0. And therefore, we had some terms that we are using, which are describing the characteristics of this matrix. One of them is that the matrix is singular, okay? Therefore, not invertible. And the reason for this, if you look at your notes, we're saying this because the problem is not completely defined or defined. You have not defined the problem completely. Therefore, you cannot have a solution. We need boundary condition. And as we say, boundary condition are not applied on an element. Remember, an element, you have extracted it from a body. Okay. So to be able to utilize the boundary condition, that's why we need to assemble back our system. And then now we input the boundary condition where they are located in the whole system. Now, to do so, to understand that stage of assembly, we are considering a spring system. Now we have come out of the spring element. So a spring system, consider if we are talking of a truss, we could be talking of a truss system. So it's composed of different parts, components, different elements. So this spring system, for simplicity and for ease of understanding, is a system composed of 2 spring elements. So in this case, we have element 1. We said element is denoted by, of course, we have the node 1, 2. So this is element 1, and you circle that number, and this element 2. Okay, you circle that. I'll try to move a little bit faster because whatever we are doing here is a repetition of last week's work. But it's because I want us to, by the time now we are assembling, I believe this is where we stop. No, we didn't stop here. We even formulated the equations. So we said, of course, this is just to define some forces, how we are relating to forces, internal force acting on either of the node. So we said for each of the elements, for each of these elements, we said that let's break them down. So because that's the first stage, we have that, okay, and we have the element 2. I've just separated them intentionally, but from the principle of compatibility, we say that, or we do not allow a body interconnected nodes to separate. Before and after deformation, they have to remain the same. That's a principle of compatibility. So node 2 have to remain the same, whether it's bent, whether it's backwards outward, whether it elongates, contract. Node 2 for both planes have to remain the same, interconnected. Now, element 1, we formulated the finite element equation. And remember what we said? We said these internal forces is what I wanted to mention here when I was breaking this down, is that we wanted to highlight that for this node 1, 2, 1, this is 2, 3 for element 2, there is an internal force acting on node 1 of element 1. And there is an internal force acting on node 2 of element 1. The same case here, there is an internal force acting on node 1. Remember, node 2 globally is node 1 for element 2, because we said for a 2-node element, right now we are just considering linear element, it's a 2-node. Of course, the node will be ij, where I is 1, j 1, I mean ij 1, 2. Okay, so node 2 globally, this node referred to as 2 in the system, for element 2 is node I 1, and then this part, this 3 is node 2. So the force acting on node 1 of element 2 and the force acting on node 2 of element 2. And we say that, of course, the summation of resonant force at this node, because we said there are internal forces and there are the external forces. And I spent quite some time explaining about the externally applied loads and the internal forces that developed as a result of the externally applied forces. We talk of the strength, ability to resist load, the applied load capacity, strength and stress. Okay, stress now, this is what developed inside the body, the material, as a result of the applied load. Okay, now the external force per node, we are representing them using capital F. Okay, F1, F2, F3. And we said for the node F1, external force F1 is the same as the internal force on that node F11. The external force on node 2 is equals to the summation of the internal force acting on node 2 of element 1 plus the internal force acting on node 1 of element 2. And of course, now F3, we said, is the external force. F3, F2, or force acting on node 2 of element 2, right? Okay, without spending much time on that, we developed the equation for 1 and 2. And then using these expressions here, we were able to now combine. Using the force equilibrium, we were able, this is by noting that the external force have to be in equilibrium with the internal force in either of the nodes. That's how we are able to come up with these relations at node 1, 2, and 3. And this is the method we are saying assembly, using the method of force equilibrium concept. Okay. And of course, now, once you understand that, it's just a matter of putting down what you have formulated for each of the elements, and then rearranging them, maybe to have U1 starting, U2 coming number 2, U3, and so on. With that, we wrote in matrix form. Of course, it's just this equation of capital F1, F2, F3 that we are assembling. Remember the capital F1, F2, F3, these are for the structural system, not of the element. So in matrix form, we ended up having this equation, which we are calling the global finite element equation, the global, now for the whole system. In some of the textbooks, you may find the word the structure finite element equation, because this is no longer a finite element equation for the element. It's not elemental, it's for the whole structure. So you can either use the word structure or the global. And as I said, now here you can see I'm using a different notation by just typing them in bold. instead of using the braces. So for your handwritten computations, you have to write this. You have to write this using bracket. Like I would have written K, then square bracket like that, U like that. This is a displacement vector, and then capital F, which will be a force vector. Okay. So far, so good up to that point, I believe. Since I'm not getting any question, I think we are comfortable. Okay, I proceed. So K is the stiffness matrix for the spring system. So we have been able to get the global stiffness matrix. And as you can see, this stiffness matrix is a 3x3 matrix. Okay, and we have just introduced one more element. You can imagine now if we had a system of a number of springs, how wide, how the order of the matrix, of the stiffness matrix. And you see, based on the order, it means we are solving the equation with all those unknowns, U1, U2, U3. Okay, by now I know things have started going out of hand. Because now if I tell you to solve this using Cramer's rule, using method of resolution at joint, I mean, not sorry, method of substitution, it's quite some hard task. So if we go to 4x4, then things become a little bit complicated. So we are restraining ourselves for purposes of understanding with two elements. And I say this is why now the power, we need to harness the power of computers or computing powers when the structure now become, when we are dealing with real structures with many elements. There is another method that you could have used to come up with the finite element equation, and I believe this is where we stopped last time, which is called the superposition method. We started with a bit lengthy, let me call it lengthy method, but the beauty with it is that it's from first principles. It's very easy to follow. Now, there is another one which is an easier method, but you have to be careful. Let me draw that disclaimer at this point. You have to be careful that you do not confuse or you do not start adding things which are not supposed to be added together. We call it superposition method. And this method is enabled by the fact that, or what we call the principle of compatibility, okay? That nodes at the same point, I mean interconnected node, in this case is our node 2, remain at the same point. Therefore, displacement, whether we get the finite element equation or the stiffness matrix, because the first thing that we do before we get the equation is the matrix, the stiffness matrix, is that at the common node, they remain interconnected or they remain connected, whether no matter how much they deform. By deformation, we are saying even if this one elongates like that, even if let's say something like it's bending like that, okay, the common nodes remain connected. Therefore, we can be able to sum the deformation of that common node is summation of the deformation for different elements at that node. Okay, let's see this clearly. So we are saying to use this method, you can enlarge the stiffness matrix for element 1 and 2. Let me show you using a very simplified way. Okay, and maybe I may need to just go back to where we developed the equation. Yeah, allow me to come here. Or without even coming there, let me just go to where this superposition. Without enlarging, I want to have the two matrices. We know I want you to have this because this is what you'll be doing. Okay, something like that. We know that we have 3 nodes. So using a pencil or something very faint, because these are just guides. This is not part of the equation. So let me maybe write using a different font. So U1, U2, U3. Okay, and of course U1, U2, U3. Okay, so using a pencil, you can just partition this. Okay, this may seem different from what is in that book, but I'm just giving you a very simplified method of doing this. Once you partition this, okay, Now, this is the stiffness that we want to compute, the global stiffness matrix. So we have for K1. So you come and say for K1, how is K1? K for spring 1 is equals to K1 minus K1, K1 minus K1, K1. Okay. How does this behave? Okay, let's also put for K2. K2 is equals to, of course, this one you have them already. So K2 minus K2, K2 minus K2, K2. Okay. Now with that, you know that element 1 have got node 1, 2. So this is U1, U2. And this I said in the pencil, it's not part of the equation. Don't confuse this. And then this is U1. For K2, this is U2, U3. This is, of course, U2, U1, U2, U2, U3. So superposition principle. We just come at this point. This is now for the global stiffness matrix. We are looking for element, the value of K for U1, this part. U1, U1. So we come to our matrices. Where do we have U1 in element 1? U1 is K1. In the second K2, stiffness matrix for K2, and this one you have to put them in bracket, otherwise they'll confuse you. You just think is the stiffness of the springs. Okay. So K2, we do not have U1 there. So this one remains as K1. Now the second, this cell, you can call it cell or this element. Let's say cell, because now, of course, when you're dealing with matrices, you talk of element. The entries in the matrix are called element. But now, since we are talking of finite element, and the word element already is being used to refer to these small bodies, let's use the word member or the cell. Let's refer to the cell. So U2, U1. We go to our original elemental matrices. Where do we have U2, U1? We have U2, U1, this one, in the first matrix. Do you have U2, U1 in the second? No. So this one becomes minus K1. Then the third one is U3, U1. Of course, you can't get U3, U1 because they are not interconnected. Okay. Node 3 is not shared by element 1. So that's why we have that as 0. Okay. Then we come to U1, U2. I hope somebody is following this. U1, U2. This is this part we want to fill in here. U1, U2. U1, U2, we have U1, U2 in element 1 as negative K1. Do you have U1, U2? No, in the second element, you do not have U1. Why? Actually, it's because for the second element, U1 is not a shared node. Okay. So this, we just have one value minus K1. Okay. Then U2, U2, this is where we have some computation to do, or some consideration, because this is a shared node. And we are going to see this by noting that in either of the elements, K1 and K2 matrix, we have U2. So U2, this is U2, U2. U2, U2 is K1, right? We come on this side, so we write K1. This is superposition principle. So K1 plus, in the second elemental matrix, for the second element, U2, U2 is K2. So this is K1 plus K2. You can see the principle of compatibility. Shared nodes, it's remain together. Therefore, the contribution of element 1 and element 2, we are summing them up. Now we come to the third entry in the second row, U3, U2. Of course, we don't know how U3 in element 1. So U3, U2, we have minus K2. And following the same, you'll find like Q1, U3, there's no share node, so 0. U2, U3, you find this minus K2. And U3 is K2. You see? This method is a little bit faster, but you really have to be careful about the nodes, how you have arranged your matrix. And that's why from the word go, I said, let's arrange the displacement and the case. Let's follow some order, some sequence, 1, 2, 3, instead of just having them two. Because not always will you have a system like this, okay? Like they are following 1 and 1, 2, 3. When we come to a truss like that, you'll be having 1, 2, 3, okay? Maybe you have 4, you may have 5 somewhere, something like that. So you find like when you write down the stiffness matrix for an element, you really need to observe the order so that when you come to addition here, you are not confused when you have about 4 or 5 different matrices where you are looking for, we have U1, U2 in the first one. You may end up missing out on some of them. But this is the easiest method. So this is the stiffness matrix, capital K, for the global, okay? And to convert this to finite element equation, you just need to introduce what? The force vector and the displacement vector. So this is an easier way. You may follow that, or you may follow what I've listed here in this in the notes by expanding where we do not have those values. This is U1, U2, U3. In U3, for the first element is 0. So doing so, you end up, this is the matrix. The same matrix that you are looking at that I have just developed is the same matrix here. And I'm saying now, by just introducing the force vector, U1, U2, U3, you see, you cannot even introduce the force the displacement vector, U1, U2, U3, if you did not arrange these matrices in the order, U1, U2, U3, okay? Then force 1, okay, force 1 and 2, this is a combination, and for this one you found from the force vector. And this is the same equation that we derived using the force equilibrium. Let's see now to the third step, how do we solve for the unknown? What we solve for the unknown, which are the displacement, the forces, we introduce the boundary condition. Now, to do this, we are adding some information. Remember, I said that if a body like this, if you apply a force on node 1 and a force on node 2 and node 3, and it's not restrained, it will float on space. There will be no deformation. It will just move on space, unless the forces are opposing one another. Like on this side, on the node 1, we have tension, on node 2, tension. But if it's compression, the way like we are showing using the arrows, then this spring system will float in space, what we call a rigid body motion. To avoid that, that's why we provide adequate restraint. Okay, it's the same thing that you have doing in structural analysis 1 to, I believe, 4. If there was the issue of redundancy, there was the issue of the problem not being well defined, if the boundary conditions are not well stated. So we are assuming, or we are considering that the force that I was showing, force 1, is as a result of reaction. So meaning the node 1 was fixed, it's a fixed head. And of course, now the force is applied on the other side. Now we are saying for this case, these are just additional information. If we fix, of course, because we want to introduce boundary condition and load condition, for this body to deform, for the spring system to deform, it means there is some applied force, externally applied force, okay? And for this case, it's assumed that on node 2, we are applying external force, F2. On node 3, there is an applied force, F3, just the same force that we had. On node 1, we did not have a force, but if it's fixed end, then it means we have a force 1, which is the reaction, as a result of the applied force on node 2 and 3. Due to the fixity at node 1, then it means we cannot have deformation at node 1. So U1 is equals to 0. So in our equation, you just need to substitute U1 is equals to 0. Then we are left with U2, U3. F1 is unknown, is the reaction. F2 is a numeric value, which is known P and P. So this one now you can simplify. What we do here, where we have a degree of freedom equals to 0, first we remove those rows. The row associated with U1 and the column associated with U1. We are holding them back. We use what we call row reduction. Row reduction. So we are left with this matrix. This is a 2 by 2 matrix. You can comfortably solve this. Okay. So this is what we are saying, row reduction. It will reduce to this. It will reduce to this. And of course, now this one, very simply, you can solve this simultaneous equation. I won't go into detail because I believe you revised your matrices operations. So you get, in this case, you can get the U1, U2, and F1 as given here. U2, U3 is equals to this in terms of P. Remember, P is a value. It could be 2, it could be 20, it could be 300 kilonewtons, and so on. And the reaction force F1 is found to be negative 2P. And you see, if on node F2, using the principle of equilibrium, if node F2, we have force F2, force P, and node F3 we have force P. So the total force pulling this spring, which is fixed on node 1, is P plus P, 2P. Therefore, we must have an opposite equal force as the reaction, which is equals to minus 2P. Good. And that's all. Let's move now to a numeric example. This is what you have in your notes. We are making matters a little bit more interesting now that we have introduced the third spring. So you're given a spring system shown. You're given now the values of stiffness for each of the spring. K1, K2, they are given values. K1 and K3 are the same. K2 is 200 Newton per millimeter. A force is applied at node 3, which is 500 Newtons. And now this is something that nobody will be telling you, okay? The information here about the displacement, right? Nobody will be telling you this because you are supposed to infer, to deduce. By the way, the way this system is fixed, you should be able to know what will be the displacement at the height of a node. Which one do we know? So we can see the spring is fixed on this node 1 and node 4. Therefore, U1 and U4 is equal to 0. So you are required to find the global stiffness matrix, displacement at node 2 and 3, the reaction forces at node 1 and 4, and the force in spring 2. The force in spring 2, the one in, so there's an internal force, okay? It's not force at the nodes, not external force applied at the node, but the internal force. Now, you may not be told all these things. We have broken down this so that you may understand. But if I just came and told you to calculate the force in spring 2, you may find like you have to undergo all these steps. So let's start and move fast now that we have been able to understand the concept as well as we've looked at an example case. Now, the elemental stiffness matrix, this is a no-brainer because we know it's K for element 1. So here, what you have is that this is element 1, this is element 2, this is element 3. Okay? So for element K1, we have K1 minus K1 minus K1, K1. You know that. That should be at your fingertips by now. That for a two-node element, spring element, the stiffness matrix will be K minus K minus K, K, okay. Okay. So what is K for 1? It's 100. So this is 100 minus 100 minus 100, 100. The second one, K2, 200 minus 200 minus 200, and so on. Then you apply the superposition principle. I said it's the easiest of them all. So how do we go about this? We have, so what I'm going to do here is that I'm going to make, I know there are how many nodes? 1, 2, 3, 4. U1 up to U4. Okay. And for K1, it's the node. So this is between U1, U2. Okay, U1, U2. This is U2 for K2, U2, 3, the nodes 2, 3, U2, U3, U2, U3. Again, for K3, you see, K3 have got node 3, 4. So this would be U3, U4, U3, U4. I keep on repeating this because I've seen the student making this mistake always. These values I'm writing at the top are just to guide you. They should not, actually in an exam setup, don't write them using a pen. Okay, they are not part of the equation. I would prefer even after you're done with them, you remove them. Right? These are just to guide you. So I have U1, U2, U3, U4. Okay. So I'll have something like that. U1, U2, U3, U4. Now, having said that, we can now start superimposing or addition of common terms. U1, U1. So we have for element 1, we have of course, this one you can just go without saying. Node 1 and node 4 are not shared with any element. Element 1 is the only one that has node 1. Element 4 is the only node that have. It's not. The element 4 is the only element that have node 4. So it means they are not sharing. So I come to element 1. U1 is 100. U2 U1. As long as I see U1, I know it's only occurs in one of the in node 1. Then I can come to U1 U2. Let me start now going down one. U1 U2 is minus 100. Okay. Where am I getting this value? U1 U2 is this value. U2 I know there's no more U1 with U3. So U1 U3 is 0. U1 U4 is 0. But I even can go around on the top row. There is no U3 U1. There's nowhere U3 and U1. Even if I go through all this, what is guiding me is that because I know as long as I say U3, I'm talking about element 2 and 3. They have shared nodes. So as long as I'm talking 1 is not shared with either of them. It's not shared in U3 and U4. So this one becomes 0, 0. But even without that prior knowledge, if I don't know that, I just need to be very careful. I come here, see in K1, element K1, elemental stiffness matrix K1. See that this elemental stiffness matrix K is written in bold. In your writing, should be having a square bracket because it's a matrix. Okay. Unless, of course, if you have superpowers, you can be able to write in bold. So I come to U2. U2, of course, is shared. So I come to the first element. You have U2. I'm looking at U2. From the first one, I have U2 is 100. So I have 100. Okay. Then we have U2 in the second one. U2 in the second one. This is 200. Okay. So plus 200. Do you have another U2? No. So I move to the next one. And like that, you can be able to fill up this matrix completely. So you see, we're talking U1, 100 minus 100. U2, we've gone up to this part. We've been able to do a hard calculation to this part. So the other is just a matter of to see where there is. They have common nodes, and then you're adding them together by just extracting them from this element. All, of course, now after you do addition, you can add 100 plus 100 is 300, and 200 plus 200 is 300. So you add that and you end up having this as the stiffness matrix. One of the feature of this stiffness matrix is that it's always, as I said, it will always be symmetrical. Along the main diagonal, everything on this side is the same as on this side. This element is the same as this element. This 0 at this corner is this 0 at this corner. Okay. Number 2, symmetrical, and it will also always be square. The number of rows are equal to the number of columns. Okay. I don't know whether there's any other information I need to say at that point. Now, once you have done this, what remains is just to introduce. If you want to make to have the global finite element equation, you just introduce the force and displacement vector. So this is the equilibrium equation. The word equilibrium equation is also the same as the finite element equation because it's using the principle of equilibrium. So this is what we had. This is what we had as K. Okay, the capital K for the global. Then we just introduce the displacement vector and the force vector. Okay, the force vector. And doing so, you are able to come up with develop or to obtain the final equation. So to solve this equation, step number 5, we introduce the boundary condition. What did we know is that due to the edge fixity here, we said U1 and U4 is equal to 0. Number 2, looking at what was already given, let's go back to our question. Okay, what was our question? Our question was P. There is a force P applied at node 3, which is equal to 500 newtons. So it means at node 2, if there is a force F is equal to 0. So these are things that you deduce by observation. So F3 is equal to P, F2 is equals to 0. And then we have F1 and F4 are unknowns. Once we do that, we can use what the term you're saying, row reduction, where we have, of course, we say the U1 and U4 is equals to 0 because of this fixity. So this is 0, and this is 0. So we can remove the rows and columns associated with U1. So the first row, the first column is associated with U1, and the fourth row, as well as the fourth column, is associated with U4. So you are left with just this 2 by 2 matrix. So using that by deleting first and the fourth rows, I prefer to say row reduction, or reducing, deleting the row, whatever the term that you want to use. Remember, this is not the same as the row reduction we're using in solving simultaneous equations. Because although we have removed them at this stage, we are still going back to them, because when you come to calculate F1, we'll need to go back to the equation 1. When you come to calculate F4, we need to go back to equation 4, right? So with this now, of course, I know now this one is very easy. You just need to get the determinant of this. You get the inverse. On this side, you'll be left with U1, U2, U3. So, and with that, you're able to get U2 is equals to P over 250. U3 is 3P over 500, or U2 is equals to 2 millimeter. U3 is equals to 3 millimeters. It's equation 6. What was the other part that we are required? We are supposed to get the reactions at node 1 and 4. So you go back to equation. So this global equation, you take the equation for F1, it's the top row, and the bottom row, F4. So you end up having F1 is equals to, now you're just substituting, okay? Let me go back there one more time. So you see F1 is 100 U1 minus 100 U2. The rest is 0. 100 U1 minus 100 U2. What is U1? U1 is 0. So F1 is minus 100 U2. And this is here. This is it. F1 is minus 100 U2, and U2 is 2. So F1 is minus 200N. Same case with F4, you can be able to compute that, minus 300N. And you can see, if there was a force applied in the positive x direction at node 3, which is 500 newtons, then using the principle of equilibrium, the summation of forces to be equal to 0. That's why you are seeing this one being negative. This means they are acting on the opposite direction. Remember, don't forget this, that this is the positive direction. In our axis, this is the positive. Okay, positive x, positive y. Okay, we are going to see something very interesting when we come to the beam, whereby the notation we may need to refer to the notation that we are accustomed to. When it comes to finite element method, the notation changes. But of course, we cross the bridge when we reach there. This stage, just know that the positive x direction, anything negative, it means it's on the opposite direction. So this one, it means it's trying to counteract the force that is applied on node 3. So the second one, we move with speed because we have less than 10 minutes or so. Now, we want to get the internal force for element 2. So the internal force are the small letter F. So what do we do? How do we go about this? We go about by, we come to spring 2, we get the finite element equation of that single element. And if you can recall, we are talking of Fi, Fj. So this would be K2 minus K2 minus K2, K2, U1, U2. Ij, I is 1, J is 2. I is node 2, J is node 3. So the internal forces at either of these node F1, F2, of course, they have to be equal and opposite each other. Okay. I don't know whether so far at that point you are together, so that I can just refresh, take you to where we got these. I'm going to where we started the lecture today. You remember these equations? Okay, right? You recall these. If you do, then this is where we are developing the elemental stiffness, elemental equations. Okay. Now, Any questions so far up to that point? Not having any question meaning we are comfortable. So this is now the elemental. We are going back to elemental stage. Of course, we have solved the global equation. We have gotten even the reaction at the support for the system. So now here at this point, we want to now like to retrieve or to let me take you here. I like referring student to past notes. Do you have that? Okay. Finite equation element generation. General steps. Yeah, this one. Okay. So you see, we are at step number 7. 6, we have solved for unknown degrees of freedom. These are the displacement at the nodes. We have solved them. We are at step number 7, solving for elemental stresses, strains, and any other derived quantities. Okay. So derived quantities, I'm looking at your nodes. Derived quantities may include or will include the internal forces, because once we determine the internal forces, it's only that for the spring element you are not calculating the stresses. Okay, so for the internal forces, I'm going very quickly to where we left. The internal forces, once you get the internal forces, if we have the cross-sectional area, we can get the internal stresses and the strains as well. Okay, now with that, once we have been able to obtain the elemental equation for element 2, it's just a matter of substituting. So here, I is equals to 2, J is equals to 3 for element 2. So you can calculate the spring forces. U2, of course, the nodes UI, UJ is U2, U3. We have calculated what is 2, what is 3. And in so doing, you can be able to calculate F, either of them, because we know that the force, these two forces, it will be equal. Summation should be equal to 0. So they will be equal and opposite. So either one of them that you choose to, whether you want to use the top row, whether you want to use the bottom row, you're going to get the force in the spring. It's 200 newtons. And that's it. It's very simple. As I said, this is one of the easiest and the simplest of the theory of structures that you have ever handled. I would like to stop there with this as a workout example. So what you need to do here we are just testing whether you can be able to arrange. You are able to arrange. The question is, for this one, this system, you are told to find the global stiffness matrix. Actually, you are not solving anything. You're just told to, can you be able to assemble? Because for either of the spring, you know, is K minus K minus KK. Can you be able to use whether the superposition principle? Actually, the superposition principle is the best. Yeah, even the forces given F1, F2, they are not necessary at this stage because the requirement is just find the global stiffness matrix. So can be able to develop that large matrix. So as a guide, what you do here, of course, the nodes have been labeled as 1, 4. This is 4 node 4, node 2, node 1. Of course, they have been labeled arbitrarily. So the same way we have done. So this one will be long. This one will be lengthy. Because you have how many nodes? We have one node 4, 1, 2, 3, 4, 5. We have 5. So you'll be having to U1 all the way to U5. And then you're going to prepare for both element 1. And you see for element 1, the node is not 1, 2, it's 4, 2. Okay? So you may need to rearrange it to be 2, 4, something like that. So this is to test whether you can be able to confidently. Actually, it's a matter of just being careful to follow the steps that you have listed or outlined in the proceedings that we have had today. Okay? So try that. I like to see the type of answers that you get when we meet next week, of course, I'm going to share the answer to that, but I want you to try it first. In addition to that, I also want to give you another challenge as a practice. So you are given this equation. Okay. So this one, maybe you can take a screenshot or you can refer to this later on, because of course it will always be archived in this video. You have a system of one-dimensional springs. This is the global stiffness equation. Sorry, global stiffness matrix, not equation. This is the global K. Yeah. You can see they have all the way up to 6. So you have 6 elements. Now you are requested to draw the system of springs. Again, there is no procedure in terms of like a formula that you need. This is just a matter of knowing. There is a principle of compatibility, which nodes are shared. Like now you can see K1, K2, K3, K4, K5. This one tells you all these nodes are sharing. I mean, element 1, element 2, element 3, element 4, element 5 are interconnected. Okay. So try that also, and then you see the typical answer that you expect to get next week. If I don't have anybody who will have attempted by next week, I'll also not give my answer. So let me get at least 1 or 2 attempts. Okay. That's it for today. I was looking at the chat to see whether there's any question. No question. I don't know whether there's anybody who would like to answer a live question in the remaining 8 minutes. We have about 8 minutes. So what I can do is I can exit this. Yeah, can exit this, and then I try to share what we have. Yeah. So in the meantime, if you have any query, any concern, make sure you register your attendance. Make sure you register your attendance by just leaving your registration number, unless where your name is not the one that you are using for. If your name is not the one that you're using here, is not the one that you have logged in with, I believe you can write your name. Now I'm doing this so that I can be able to exit this. Now this is a bit tricky when you are projected. It requires you to go to the last slide. Yeah, good. I'm sorted. So what I wanted to do is any question either this week or last week's work, we can address it here. So what I was saying is I'm on Zoom on this side, but of course my Zoom can only allow a few people. So what I do usually, I'm going to share with the class lab for somebody who might want to ask a question. In the remaining 7 minutes. Class rep, I have shared the links for Zoom, but it's only for those people who or for somebody who feel that he want to ask maybe something he cannot be able to express it well in written form. You can join me there and then you ask the question. Of course, I'm not going to exit the live stream. Okay, I'm not going to exit live stream because the question asked will be answered live here. So you only have about 6 minutes. If you have any question, if you have any comment, you can as well leave it there. Okay. So in the meantime, let me also know whether you have any challenge, whether you have been able to, for our assignment, whether you've been able to download the Abacus software. Okay. The Abacus software. Thank you. There is a question by Susan Mutuku asking why was F2 equals to 0? F2. You see, the capital Fs are externally applied forces. Okay? Externally applied forces. So there is no external force applied on node 2. Now, from the last calculation, that we have had, we were able to get the internal force at node F2. So the external force F2, we did not calculate the internal force at node F2 due to element 1. So this one tells you the internal force at node 2 due to F1 and the internal force at node 2 due to F2, the sum of them is 0. So F2 is externally applied force, and there is no external force applied on node 2. That's why it's equals to 0. Okay. Are we in agreement? Good. So I'm just waiting to see whether there's anybody with a question here. In the meantime, I don't know whether we can be able to create a poll here. Okay. Okay. Let's see. Understood. Thank you, Susan. Thank you. I understood that. There's that one question that okay. I'm just want to take a short poll. I don't know whether it's visible from your end. As we end the class, you can comment there. Of course, if you have any question, let alone we can continue engaging. So thank you for joining on time. Thank you for your participation. Let's continue gaining more knowledge. So that's the end of our class for today. We meet next week physically. We meet next week physically. There is a poll that I've just listed there, just for purposes of evaluation. Janice, you are saying Anyago both. I left that one intentionally. Yeah, because I was asking specifically for this class. But I would like to know for online classes, I just wanted to get the weight. Which one is weightier? Okay. All right. Class dismissed. We meet next week. Feel that comment, leave any comment. Later on in all the videos as you watch, you can leave a comment there and then we can be able to respond to. Thank you. God bless you.